Hi folks, we're going to take a look at question 12 from page 110. So here they give us the equation of a line, and they give us the equation of what they tell us is a sphere, and they ask us to see if there's any intersection between the line and the sphere. Okay, now here, we talked about this in class, how this equation looks a lot like the equation of a circle. So if we took something like this, we'd have x squared plus y squared equals, well, 6 would represent the radius squared, so radius would be √6. Okay, but if we add in this extra component, what it gives us is it gives us a sphere in 3D. Okay, the exterior part of a sphere. Okay, and we make the reasonable assumption that that must still represent the radius squared. Okay, so we'll keep that in mind. But for now, we just want to determine the intersection between these objects. Okay, and you don't really even need to know that this is a sphere. But since we do know, let's think about it. Okay, so if you have a sphere and you have a line, and you realize that if the line goes through the sphere, well, you're going to have 2 points of intersection. Okay, the line might not go through the sphere at all, so there might be 0 points of intersection, or it could be tangent to the sphere, in which case you would just have 1 point of intersection. So even before starting, I know that I might have 2, 1, or no solutions, and that should make me think about solving quadratic equations. So I shouldn't be surprised if in this process I have to solve a quadratic equation. Okay, let's get to the problem itself. We're looking for a point of intersection, so it means that whatever x, y, and z components of a point of intersection, that'll be on both the sphere and this line. So we're going to do what we normally do when we're looking for a point of intersection, is we're going to equate the things that should be equal. Okay, so the x value here should be equal to the x value there. Same with y, same with z. So let's write out, okay, using parametric form, let's write out what the x components of a point on that line would be. So the x component would be, well, 0 plus t, so just t. The y component would just be 5 minus 3t. And the z component would be 3 minus 2t. And what we can do is, in this equation for the sphere, replace x, y, and z by these components. Okay? Since the points we're looking for have to exist on both the line and the sphere. And when we do that, so we'll start with x squared, so t squared, plus 5 minus 3t squared, plus, whoops, forgot the bracket there, plus 3 minus 2t squared equals 6. Well, I end up with an equation with only one unknown. So I should be able to solve it, especially since I realize that when I expand everything, this will just turn out to be a quadratic equation. Exactly what I was expecting to solve based on my diagram. So let's here, t squared plus, and here, either write out 5 minus 3t times 5 minus 3t, or remember the song you might have learned back in grade 10 or 11. So square the first, square the last, twice the difference of, twice the product of first and last. Okay, so twice the first, 25. Okay, twice the product of first and last, so 5 times minus 3, negative 15 times 2, minus 30t. Okay, then plus square of the last, 9t squared. Okay, let's do the same thing here. That'll give me 9 minus 6, and 6 is 12t, and then 2t squared, so 4t squared. Okay, is equal to 6. Let's bring together everything on one side since it's a quadratic equation. So 1 plus 9 is 10, plus 4, 14t squared. Here we have negative 30 minus 12 is negative 42, so minus 42t. Then we have 25 plus 9 is 34, and then minus 6 from the other side, so that's plus 28 equals 0. Okay, and I hope that you won't just jump in and use the quadratic formula here and notice that these three numbers are all divisible by 14. So I'm going to take out that 14. I'm left with t squared minus, that's 3t, and then plus 2 equals 0. And that's so easily factorable that you really shouldn't be touching the quadratic formula here. So this will be t minus 1, t minus 2. Okay, so that means t is either equal to 1 or t is equal to 2. Okay, so this tells us that there's 2 points on this line that will also be on the sphere, meaning there's 2 points of intersection. Okay, so let's calculate those points of intersection. So point 1, okay, we'll stick t equals 1 into my parametric equation here. So we have 1, and then 5 minus 3 is 2, and then 3 minus 2 is 1. Okay, and then P2, let's stick in t equals 2, so we have 2, and then 5 minus 3 times 2, so 5 minus 6 is negative 1, and then 2 times 2 is 4, so 3 minus 4 is also negative 1. So these are my 2 points of intersections. Now, the other part of this question asks us whether these 2 points, okay, form a diameter. Okay, so in other words, are they perfectly aligned on either side, okay, where they're a diameter? But of course, they could also be 2 points here, in which case they would not be a diameter. And the way we can check that is by finding the distance between these 2 points and see if it's equal to the diameter. So the first thing here is to recognize that the radius, as we said before, would just be square root of 6. So that means the diameter is 2 times square root of 6. And let's see if the distance between these points is indeed 2 root 6. Okay? So we want to find the magnitude of the point P1 to P2. Not the point, sorry, the vector joining P1 and P2. So let's find that vector here. So 2 minus 1 is 1. Negative 1 minus 2 is negative 3. And then negative 1 minus 1 is negative 2. Okay, and the magnitude of this vector here will be 1 squared plus negative 3 squared, 9, plus negative 2 squared, 4. So that'll be equal to 10, 14, square root of 14, okay, which is not equal to 2 root 6. So, oops, sorry, let's show you that there. So that's not equal to 2 root 6. So P1, P2 is not a diameter. Okay, and that's it for this question.